Hello, guys. Good afternoon. We are going to start this discussion/review session. The agenda for today is this. First, we will answer questions you might have for Lab 4. And then, if you don't have any questions, we will start solving the questions of the midterm exam. You can ask anything, any questions you might have about this exam. And in the end, always, only if we have time and you are eager to do that, we can continue solving homework 4 and homework 5. So it's time for questions in Lab 1. Lab 4.
Okay. So I'll just start with the first question of the exam. Let's read it first. Computer scientists at ETH developed a new memory technology, ETH-RAM, which is non-volatile. The access latency of ETH-RAM is close to that of DRAM, while it provides higher density compared to the latest DRAM technologies. ETH-RAM has one shortcoming, however. It has limited endurance. That is, a memory cell stops functioning after 10 to 6 writes are performed to the cell. So the endurance of its cell, based on this statement, is 10 to 6. A bright ETH student has built a computer system using 1 gigabyte of ETH-RAM as main memory. ETH-RAM exploits a perfect viewer leveling mechanism, that is, a mechanism that equally distributes the writes over all of the cells of the main memory. The first question. The student is worried about the lifetime of the computer system she has built. She executes a test program that runs special instructions to bypass the cache hierarchy and repeatedly writes data into different words until all the ETH-RAM cells are worn out. All here means the whole set of 1 gigabyte memory cells. And the system becomes useless. The student's measurements show that ETH-RAM stops functioning in 1 year. That is 365 days. Assume the following. The processor is in order and there is no memory level parallelism. It takes 5 nanoseconds to send a memory request from the processor to the memory controller, and it takes 28 nanoseconds to send the request from the memory controller to the ETH-RAM. ETH-RAM is word addressable. Thus, each write request writes 4 bytes to memory. So, we have 1 gigabyte of memory cells. We assume 1 gigabyte is equal to 2 to 30. There is no problem if you assume 1 gigabyte is equal to 10 to 9. But here we assume that this is 2 to 30. And each memory cell should receive 10 to 6 writes. So the total number of writes would be 10 to 6 by 2 to 30. This is the number of writes that should be performed on the memory cell, but with each write request from the processor, you can write 4 bytes, right? So what is the number of writes from the processor? You should divide it by 4, or 2 to 2. 2 squared. What is the latency of these writes based on the problem specification? That would be T ETH RAM. That's the time required to write a word to ETH RAM, plus the time that you need to send your request from your processor to the controller, and from controller to the memory module. So this is the time that it takes to, then this is the lifetime of our ETH RAM. And based on the problem specification, this would be equal to 1 year. And since all the numbers of memory accesses here are in the orders of nanosecond, we multiply these by 10 to 9. So this is our equation. So the latency of writes to the ETH RAM would be the result of this equation. Right? Yes. There is no problem if you just write this equation. Yes, you can make an approximation, and there is no problem with that approximation. Yeah. Actually, the important insight in the problem is that you understand you need 10 to 6. You understand that all the memory cells should be written, and you understand that with each write, you do 4 bytes, right? And the other is that since we do not have memory level parallelism, the access would be the sum of these factors. B. ETH RAM works in the multi-level cell mode in which each memory cell stores 2 bits. The student decides to improve the lifetime of ETH RAM cells by using the single-level cell mode. When ETH RAM is used in SLC mode, the lifetime of each cell improves by a factor of 10, and the write latency decreased by 70%. What is the lifetime of the system using this SLC mode if we repeat the experiment in part A with everything else remaining the same in the system? Here we should repeat those calculations that we had for part A, but we should consider the conditions that are specified in the problem. First, you're using SLC instead of MLC. So SLC stores 1 bit per cell. And that means that your capacity is decreased 50%. This is store capacity, and each memory cell will require 10 to 6 by 10, since the lifetime is increased by a factor of 10. So we need 10 to 7 writes per memory cell. The other parameter that we should consider is the latency of write for SLC. The problem specifies that it is decreased by 70%. So the final latency would be 0.3 or 30% times T ETH RAM that we had here, right? So the final answer would be multiplication of these numbers, 2 to 29 divided by 2 to 2 times 10 to 7 by, we already estimated this, that would be around 25.35 nanosecond. So that would be 25.35 plus 5 plus 28. And if we continue this calculation, that would be around 2 to 2.49 years. So if we use SLC instead of MLC, the lifetime of system would increase from 1 year to 2.49 years. Any questions? Yes? Right. Yeah, there is no memory level parallelism.
Is memory level parallelism assuming that there are like multiple banks?
Can you repeat your question? So we mean that, we mean that each request from the processor would be executed in serial. There's nothing about memory level parallelism within banks or within memory chips. You receive a request, execute, and then the next request.
Okay, even if there is like no bank parallelism, but the request can be overlapped.
How? When you execute our requests sequentially, overlapping happens when you can execute 2 requests in parallel, right? You have request 1 and request 2 in the queue, and you can overlap their execution in bank 1 and bank 2. But here, in the problem specification, we clearly mentioned that the processor is in order, and there is no memory level parallelism. We do not issue parallel memory requests. Right? Okay, we can move to second question. It's yours.
Okay. So question 2 is cache performance analysis. In this question, what we do is do some micro benchmarking. This means that we are going to execute a specific program, short program, that is going to exercise some particular features of the cache hierarchy. It's very interesting. This kind of micro benchmark is very useful because it usually allows us to do some reverse engineering in systems that we don't know how exactly they are built, and after getting this knowledge, we might be able to optimize our code, for example, better. So as you can see, for this micro benchmarking, we are given 2 codes, code 1 and code 2. And we are going to access in these codes to one array data that contains 4-byte elements. So it's 32-bit unsigned integers. Yes, there is a note here that says, in order for you to know, don't care about that, that this latency array, the accesses to this latency array where we are going to store the latency of each memory access is not cache. So these accesses bypass all the caches. And timer, as the question says, it's going to return a timestamp. So if we go through code A, we will see that we go through the array data with a certain stride, and we record the timestamp in the right before the memory access and right after the memory access, and then this way we calculate the latency. In the code number 2, we have 2 loops. The first loop is similar to code 1. Actually, both loops are the same. The only thing that changes is the size that we are accessing. Here is size 1, and here is size 2. With a stride 1 or with a stride 2. But as you can see, is in this loop 2 where we are going to measure the number of cycles that we need. As the question says, the cache hierarchy has 2 levels, so we will have our CPU, L1, L2, and main memory. And we also know that the size of this L1 is 4 kilobytes. Part A says that we run code 1 and we obtain this chart that you can see. You can see in the screen. So in this chart, what we can read is the latency of every memory access for 64 memory accesses. Keep in mind that these memory accesses, the stride in these memory accesses is 1. So stride is equal to 1. What happens here? This part of the question asks about the cache block sizes in L1 and L2. So what happens here? We should infer what happens from the latency values that we see in the chart. As you can see in the chart, there are 3 different latency values, 700, 300, and 100 cycles. So these give us an idea of which part of the memory hierarchy is being accessed. Obviously, L1 is closer to the CPU than L2, and L2 is closer than the main memory. So it is expected that this lower latency, 100 cycles corresponds to L1, the 300 cycles correspond to L2, and the 700 cycles correspond to the main memory. And actually, exactly what happens here in the very first access, when I is equal 0, we will have an L2 cache miss. For example, this cache block in memory will be brought to L2 and also to L1. And because we have an L2 cache miss, that's why we see this latency of 700 cycles. Keep in mind that the next access is with a stride equal to 1. So it's exactly it's exactly the next 4 bytes. The next 4 bytes that are also in the same cache block. So that's why we see this shorter latency of 100. And we see the same latency for the next 7 accesses. And right after that, 300. The latency is 300. So this gives us the answer actually for at least for the cache block size in L2, which is for 8 memory accesses is 32 bytes. So in L1, we are using blocks of 32 bytes. What happens in L2? Observe that memory access with I equal 8 has a latency of 300, so it's hitting L2. And then we again have 7 accesses to L1 because the latency is 100. So this means that another L1 cache block is being fetched from L2 to L1 with this memory access number 8. That's why we have then 7 hits. And then we have again an L1 miss and L2 hit. We are another L2 hit here, and here again we have a miss in access number 32, which is 128 bytes. And that's why we can infer that the L2 cache size is 128 bytes. Is it clear? Okay. So then let's move to part B. In part B, the question is, we are using code 2 with stride 1 equal to stride 2 equal to 32. Size 1 is 1056. You have one question? Part A. So actually, we expect from you that you answer. You explain briefly what this is about. You know, it's not just saying 32, 128. Yeah. Okay. As I was saying, in part B, size 1 is 1056, size 2 is 1024. And in this case, we observe that latency 0 is equal to 300 cycles. Keep in mind that latency 0 is the value that we obtain in this array latency for the very first access in this second loop. So latency 0 corresponds to I equals 0. So the question continues, says, however, if size is equal to 1024, latency 0 is 100 cycles. And the question is, what is the maximum number of ways in L1? Okay, we can assume that the replacement policy is FIFO or LRU for now. So we know that because we know the size of the cache, we know that there are 128 blocks in the cache, and we also know how we are accessing this array data, right? So let's say that this is our array, and with a stride, and each of these rectangles represents one block, one cache block. In the first pass, in the first loop of code 2, we are accessing with a stride 32, so this means that we read this element, this element, this element, and so on. And the question says, if the size of the array is 1056, if we are accessing up to 1056 elements, or size 1 is equal 1056, we are going to obtain latency equal 300 cycles. Observe that here, this is 1024. Observe that here we have 32 cache blocks. So the reason why we measure latency 0 equal 300 cycles when size 1 is equal 1056 is because this last cache block is replacing cache block 0. Okay? So that's why we miss in L1, but we hit in L2. In case only, this part of the question, in case only 32 cache blocks are accessed, because size 1 is 1024, this cache block is not being accessed, so it is not replacing cache block 0. So that's why we hit when we access element 0 for the second time. So from this, we infer that the maximum number of ways is 32. Okay? Fine. If you don't have any questions, let's discuss part C. So in part C, we again use code 2, and we are also going to use code 1 after that. And what we want to figure out is what is the replacement policy. We already know that the replacement policy is going to be FIFO or LRU, because that's what the part B told us. But we don't know exactly yet, so that's why we run this different experiment where we first run code 2 with stride 1 equal 32, size 1 equal 1024, stride 2 equal 64, and size 2 equal 1056. So now, in our array data, something like this again. This is 1056. 1024, this is 0. So in the first pass, in the first loop of code 2, we are accessing this element, this, and so on. Recall that we know the question tells us that the associativity is the maximum obtained in the previous part, in part B, so we know that the associativity is 32, right? So as I was saying, in the first loop of code 2, we are accessing these elements. In the second loop of code 2, now the stride is 64. So this means that we read here, and here, here, and so on. So observe that after running code 2, we run code 1, again with a stride 32, and again with size 1024. And we observe that latency 1 is 100 cycles. Latency 1 is the latency of this memory access in code 1. So if it's 100 cycles, this means that we find this cache block in L1. So even though this cache block was not accessed in the second loop of code 2, it is still in the cache. So it has not been replaced. So that's why we know that this cannot be LRU, because if it were LRU, it could have been replaced, and the replacement policy is FIFO. Is that okay? Okay. So if A, B, and C was clear, if you understood L, B, and C, then part D must be easy for you. It says, now we carry out 2 consecutive runs of code 1 for different values of size. 2 consecutive runs. In the first run, stride is equal to 1, In the second run, stride is equal to 16. We ignore the latency results for the first run and average the latency results of the second run. We obtain the following graph. What do the 4 parts shown with the arrows represent? So keep in mind that in the first part, in the first run of the code, caches are called, and we are going to warm them, right? We are going to load cache blocks in the caches, and after that we run the same code for the second time. So we are going to find some hits and misses, right? So some of the cache blocks will be in L1 or will be in L2. We might find them or not. So we will see. Observe also that the interesting part here is that we don't know exactly what's the size of the caches. Well, we know that L1 is 4 kilobytes because the question is giving us this information, but we don't know what's the size of the cache, and you obviously don't have it here in the X label. So, but it's something, it's clear. Here, latency in this part, first part, before arrow 1, the latency is 100. Between arrow 2 and arrow 3, the latency is 300. And after arrow 4, the latency is 700. So it is clear. And also keep in mind that in this plot, in this graph, we are averaging the latency results of all the memory accesses. This means that all memory accesses here hit in L1. Here we find hits in L2, and here misses in L2, and we should access main memory for all the memory accesses. So what happens in this part, even though in all these experiments, in all this flat part of the curve, in all these experiments, we have latency equal 100. What happens is that the size of the array that we are accessing is smaller or equal than the cache size, right, than L1. So you can be sure that this point here, that arrow 1 indicates, is 4 kilobytes. So this would be a good way to know what's the size of L1. That's exactly the same for arrow 3. This is the size of L2. So this experiment is good to know what's the size of L2, right? Or to confirm what's the size of L2 if we already knew that. And in these parts between arrow 1 and arrow 2 and between arrow 3 and arrow 4, what happens is that some cache blocks hit. So we have hits for some cache blocks. We have misses for other cache blocks. That is also related to the replacement policy that we are using. And the larger the array, the more cache misses that we have in L1 or in L2. Okay? So that's all, if you don't have any questions. Okay, I guess it's clear. Now, I'm going to go through question 3. Yeah, I don't know if you, this question is clear or not for you. I'm actually going to read it, and if you have any questions about that, we can discuss. So this question is about GPU and SIMD. It's somehow similar to one question you had in homework 4, if I'm not wrong. It's quite similar to that question, but it's a little bit more tricky. It's a little bit trickier because here, as you will see, the number of warps that we are going to need, I mean, then it's a discrete number of warps, but the last warp is not fully utilized. So that's the trick here. So the question says, we define the SIMD utilization of a program run on a GPU as the fraction of SIMD lanes that are kept busy with active threads during the run of a program. As we saw in lecture and practice exercises, the SIMD utilization of a program is computed across the complete run of the program. The following code segment is run on a GPU. Each thread executes a single iteration of the shown loop. Assume that the data values of the arrays A, B, and C are already in vector registers, so there are no loads and stores in this program. It says, notice that there are 6 instructions in each thread. So what does it mean? 6 instructions. Maybe we need to clarify this, because if you count the number of lines here, it's actually 7, right? The thing is that because we are going to distribute the iterations of this for loop across the threads. Each of the threads is going to execute one one iteration of this loop. And if we count, the number of instructions is 1, 2, 3, 4, 5, 6. That's why. The truth is that this is high-level code, right? The truth is that in a real GPU, the number of instructions that will be executed is higher. You agree that, right? But that's not important in this exercise, and because you're already familiar with this exercise, so I guess you were not surprised by this. Okay, it says a warp in the GPU consists of 32 threads, and there are 32 SIMD lanes in the GPU. In each of the cores of the GPUs, there's 32 SIMD lanes. It says, please assume that all values in arrays B and C have magnitudes less than 10. So the absolute value of every element in B and C is less than 10. Please answer the following 6 questions. How many warps, part A, how many warps does it take to execute this program? And the answer is 32. This is the total number of warps. Because what we are going to do, as I said, is that we distribute these 1008 iterations across threads. And even though, observe that 1008 is not evenly divisible by 32, but the last warp won't be completed. I mean, some of the threads in the last warp will be idle, but besides that, we need to run it. And you're already familiar on how the warps are scheduled and executed on the GPU hardware, so you know that even though some of the threads might be idle, we are still using them somehow, right? Because other lanes are busy, so this doesn't mean that we cannot, so we don't really launch those threads that are idle. Actually, they are somehow launched, but there's a mask in the GPU that avoids that the result of these idle threads or these idle lanes is really stored. So that's why we have to, the correct answer here is 32. Part B says, what is the maximum possible SIMD utilization of this program? Well, we have this number. The important thing is how we find this number. And the way we calculate this, taking into account that there are 31 fully utilized warps, so it's the 32 threads of these 31 warps can work because they have been assigned one of the iterations of this loop. And the last warp has only 16 active threads. So it says, in case we don't have branch divergence, this means that all the threads in the warp or all active threads in every warp are going to follow the same path, this utilization can be calculated as you can see here. So for the 31 warps that have 32 threads, and for the last warp that has only 16 active threads, this is actually the total number of threads that are going to be executed, assuming that there is no divergence in these branches, this if here and this other if here. We divide by the total number of lanes that are being used, even though you already know that 16 of these lanes for the last warp are idle, and that's how we calculated this number. Is that clear? Okay. Let's go to part C. So part C says, please describe what needs to be true about arrays B and C to reach the maximum possible Cindy utilization as in part B. So we first calculated the maximum utilization, and now we have to reason about the values of B and C, the elements of B and C that that fulfill these conditions, right? That ensure that we are going to have 100. We are going to have all possible threads in each warp active. So essentially what we have to do is doing some analysis of the code and observe that for all the threads to go through this part of the code, we need that all AI are negative. So in order for all of them to be negative, we need that the result of this multiplication between B and C is a negative, right? The important thing is not exactly what are the values of BI or CI. The important thing here is that all the sign of these arrays for all the size of, the sign, I wanted to say, there's the sign of array A for all the threads belonging to the same warp is the same. Okay, that's important. So, and it's also the same for C, right? We also need C to be negative, CI to be negative. So the explanation says we can have two possibilities. One, if no threads inside a warp take the first if, it is possible for 32 consecutive elements if the following condition is true. This BI or CI is equal 0, or BI is negative and CI is negative, or BI is positive and CI is positive. So, as you see, it is important that these conditions are true for the 32 consecutive elements, so that 32 threads in the same warp have the same behavior when executing this code. In part 2, it says all threads, so the second possibility is that all threads inside a warp take the first if. It is possible if for 32 consecutive elements the following condition is true. B is negative and C is positive, or B is positive and C is negative. This condition also ensures that for the second if, all threads take the branch or no threads take the branch. Remember that the important thing here is that all 32 consecutive threads go through the same path. Finally, for every 32 consecutive elements, we should have one of the mentioned possibilities. For the warp with 16 active threads, we should have one of the mentioned possibilities for every 16 consecutive threads. Okay? Okay, if that's clear, then we can go to part D. Part D says, what's the minimum possible SIMD utilization of this program? And again, you see the correct answer here is about a little bit higher than 1/3, but again, that's not the important thing. The important thing is how we reason about this. And the explanation says the first 2 lines must be executed by every thread in a warp. That obviously will happen because there is no control flow divergence in the execution of this first instruction where we multiply B and C and store the resulting array A, and where we evaluate if AI is negative, right? So these 2 instructions are going to be executed for sure by every thread in a warp. The minimum utilization results when a single thread from each warp passes both conditions. Both conditions means both if conditions, both branches, this first if and this second if. And every other thread fails to meet the condition of the first if. Assuming that every other thread in the warp, assuming an entire warp of 32 threads, only one thread passes the first if, and the remaining 31 threads don't pass. So that's how we will ensure that we have the minimum utilization, because the majority of the threads will be idle, right? The thread per warp that meets both conditions executes the remaining 4 instructions, but it's only one thread per warp. And now, part D asks about what needs to be true about arrays B and C to reach the minimum possible SIMD utilization that was calculated in part D. Again, please cover all possible cases in your answer. And as we have already discussed, exactly one of every 32 consecutive elements in arrays B and C should fulfill this condition, that is B is greater than 0 and C is less than 0, which actually, if you remember, what was one of the conditions that was fulfilled in part C to make sure that the threads went through the if statement and executes all the instructions in the if statement, right? So that's what needs to be true for one thread out of 32. So the explanation says only one thread in a warp should pass the first condition. Therefore, exactly one of every 32 consecutive elements in arrays B and C should have the following condition. That's the condition. So it's, actually, this is actually incomplete, right? Because it can be, this condition is B is less than 0 and C greater than 0, or B is greater than 0 and C is less than 0. That's the complete answer. However, the thread in a warp which passes the first condition should also pass the second condition. Therefore, the only condition which ensures the minimum possible SIMD utilization is exactly one of every 32 consecutive elements in arrays B and C should have this condition. Oh, exactly. This is, I was wrong. This is for the first condition. But for the second condition to be true, it's only this this one that should happen. For the warp with 16 active threads, these conditions should be true for exactly one of the 16 elements. Is that okay? Okay. And the last part, part F, says, now consider a GPU that employs dynamic warp formation to improve the SIMD utilization. As we discussed in the class, the DWF dynamically merge threads executing the same instruction after warp divergence. What is the maximum achievable SIMD utilization using DWF? Explain your answer and give us a hint. The maximum SIMD utilization can happen under the conditions you found in part E. The maximum SIMD utilization can happen under the conditions you found in part E. So remember what dynamic warp formation was about. This can be called some kind of inter-warp compaction or something like this, right? It's a technique that essentially, it's a research proposal that essentially merges threads that belong to different warps so that the utilization is maximum possible when one warp is scheduled, right? This is good to improve the SIMD utilization and to save many cycles in the execution. So, well, we can calculate this value. The explanation says DWF can ideally merge 32 warps with only one active thread in a single warp. Remember that this was the very bad situation in part E, where we said, oh, in part E, only one thread in each warp is going to be active. And this can be actually beneficial for if we had a GPU that implements dynamic warp formation, because if none of the active threads overlap with the other active threads in different warps, finally we can have an entire warp with all the threads active, right? That's the interesting thing here. So to be more clear, for example, this could be warp 0, and in warp 0 we know that this thread is active, but the rest of threads are idle. And in warp 1, maybe this one is idle, this one is idle, but this one is active. These are idle. In warp 2 is, for example, this one. And none of these active threads overlap. So in the end, what we are going to have is an entire warp with all the 32 threads active. And that's how we can definitely improve the SIMD utilization. And considering this case, which actually was the bad case, the worst case in part E, in part F, we can obtain the maximum utilization. And interestingly, this maximum utilization is even higher than the maximum SIMD utilization that we obtained in part A. Okay, if you don't have any questions, then we are done, and we can solve question 4.
Okay, question 4 is about memory scheduling. To serve a memory request, the memory controller issues one or multiple DRAM commands to access data from a bank. There are 4 different DRAM commands as discussed in class. The first one is activate, that loads the row that needs to be accessed into the bank's row buffer. This is called opening a row and takes 15 nanoseconds. The second command is pre-charge, that prepares the bank for the next access by closing the row in the bank and making the row buffer empty. It takes 15 nanoseconds. And there are two commands, one is read and one is write, for accessing the data from the row buffer, each taking 15 nanoseconds. The diagrams below, these two diagrams, show the snapshots of memory controller's request queue at time 0, that is T0, then applications A, B, and C are executed together on a multi-core processor. Each application runs on a separate core, but shares the memory subsystem with other applications. Each request is color-coded to denote the application to which it belongs. Additionally, each request is annotated with a number that shows the order of the request among the set of enqueued requests of the application to which it belongs. For example, A3 means, A3 means that this is the third request from application A enqueued in the request queue. We see here A1, A2, and A3. Assume all memory requests are reads, and a read request is considered to be served when the read command is complete. That is 15 nanoseconds after the request read command is issued. We also have some assumptions here. The memory system has 2 DRAM channels, 1 DRAM bank per channel, and 4 rows per bank. All the row buffers are closed at time 0. All applications start to stall at time 0 because of memory. No additional requests from any of the applications arrive at the memory controller. An application is considered to be stalled until all of its memory requests have been served. Now we have the problem specification. The below table shows the stall time of applications A, B, and C with first come, first serve, and first ready, first come, first serve scheduling policies. The diagram below shows the scheduling order of requests for channel 0 and channel 1 with the FCFS, that is first come, first serve, and FR first CFS, that is first ready, first come, first serve scheduling policies. And as we see here, the question asks, what are the numbers of row hits and row misses for each DRAM bank with either of the scheduling policies? To answer this question, we should consider some facts that we can extract from problem specification. First of all, if we have a miss and the row buffer is already closed, that may happen for the first access here, because here we mentioned that row buffers are closed at time 0. For this miss, servicing the request will take 30 nanoseconds. For any other misses, in servicing other memory requests, we need to first pre-charge and then activate, and then issue the read command. So we have 15, 15, 15. It means 45 nanoseconds for other misses, if miss happens for requests other than the first request of the queue. And if it is, let me write it here. And if it is a heat, we do not need activate or pre-charge, so we just have to issue read, and it would take 15 nanoseconds. This is the first fact. The second one is that from these stall time values, we can understand how long it takes in maximum to service requests of each application in either of channels. And the third fact is that a request is reordered in FR FCFS with respect to FCFS due to row buffer, to exploit row buffer locality. For example, here for channel 0, we see that B, that was the third request in the request queue, is scheduled later than C1, A3, B2, B4 when we use FR FCFS. That means that C1, A3, B2, and B4 are all row heats with respect to access to A2. So based on these three facts and some puzzles that we will have to answer this question, we will find which request is a row buffer heat and which is a miss. First of all, I have a very nice drawing for you. Let me bring it. I found that this is too small, so I have something like postmodern drawings. You see? So we know that since the question specifies that all row buffers are closed at T0, so the first access will be always a miss, right? And it will take 30 nanoseconds. The next fact, as I described before, where is it? Yeah. Is that a request is reordered in FRFCFS to exploit row buffer locality. And I gave you that example. We reorder B1 and schedule it here. So it means that C1, A3, B2, and B2 and B4 are all row heats with respect to A2 here. So we will have heat here, heat, 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 right? And based on this, I can put a heat here. Yeah, you're right. You're right. A3 is a heat, and B2 is a heat. And since B4 accesses the same row as B2, but not B3, because B3 is executed here after B1, this will be a miss, right? And also, B3 will be a miss. And since B1 is reordered here, So C1 in FCFS is also a miss, and B1 is also a miss, right? Right, B1 is also a miss here. Let me put a miss here, right? But we are not sure about A2. We don't know if it is a raw hit or raw miss. And also B3, right? So we know this will take 45, 45, 15, 15, 45, 45, and here we will have 15, 15, 15, and 45, right? So let's move to channel 1. For channel 1, we see one reorder here in FCFS with respect to FCFS. That's, you see A2 is scheduled ahead of all these requests, right? So A2 is a hit here. And from that, we are sure that C2 was a miss here, right? And C2 is also a miss here, right? Okay. This is what we can extract from these reordering and initial status of the row buffer that is closed. So now this is the time to consider the stall time of applications. Let me write it down here. And C is 135 and 90. Okay, let's start with application C. Application C with FRFCFS will stall for 90 nanoseconds. Here, we see that C2 will be serviced after 90 nanoseconds, but with C1, here, so we cannot have any information from or any solution from this knowledge because this will already take 90 nanoseconds, but here it may take 90 nanoseconds or less. So this will not determine anything about A2 here. So how about C when using FCFS? It takes 135. From these two, we know that it will take 75 nanoseconds for this channel. So this is channel 0 that determines the stall time of application C, that is 135. Here we have 30, 45, 45. That would be 120 in all. So 120, and we should have 135. So we can now understand that it was a hit here, right? For application, for request A2 in channel 0. Because if it is a miss, then this C1 request from application C would take longer than 135 nanoseconds. Right? So this is what we can extract from the stall time of application C. Now let's move to the stall times from application A. With FCFS, here we see that with FCFS, application A will take 195 nanoseconds. Let's calculate the execution or the service time of A3 here. That will be 90, 135, 165. So this is not channel 0 that determines the service time of application A here. So this is channel 1 that determines the service time of application A. That would be 195. Here we have 30, 45. That would be 75. So in all, we should have 120 more delay to service B1, A1, A2, and A3. I think we should start from FRFCFS again. FRFCFS starts, will take 135 to service application A. And from channel 0 here, we see that it will take 75 nanoseconds to service application A. So this is channel 1 that determines the stall time of application A here. That is 135 nanoseconds. This is 90. So that would be, so from here to here, based on this value, 135 nanoseconds, it should take 45 nanoseconds, right? And with 45 nanoseconds, if there is any miss here in B1, A1, A3, then the latency would be, or the service time of A3 would be higher than 45, because if one of them is miss and the other two are hits, it will be 45 plus 30. That would be higher than 35. So all of them should be hits here. This is hit, this is hit, this is hit. Right? So again, here we have hit. You're not sure. Right. A3 is a miss. A2 also is a miss because it is moved here. So it is 45. It is 45. And B1 and A1, this is hit, right? Because they are accessing the same row here. And B1, with respect to C2, here we know that it is a hit, right? So this is one more 15 nanoseconds. Okay, so the only items remaining are these, and we should consider the execution, the stall time of application B to extract if B3 here is a hit or miss, and also B2 and B3 in channel 1. So let's start with first come, first serve for B, and that would take 285 nanoseconds. Let us calculate the execution time of B here, or the stall time. This is not execution time. So 45, 90, 135, 175 plus. So this will give us 285. How about this? I mean, first come, first serve in channel 1. 45 plus 45, 90, 135. Okay. If these two are both misses, then we have. So this will not help us to guess what is happening here, right? Because this will take 285 nanoseconds, but here, servicing B4 will take 285 nanoseconds. And here, if both are miss in channel 1, then it will be maximum 285 nanoseconds. So we cannot guess if they are hit or miss here. Let's move to first ready, first come, first serve. For first ready, first come, first serve, here we have 45, 90. From here to here, it will take it will take 150 nanoseconds. So still we cannot guess the execution, the service time of B3 here, because if it is a miss, that would be 195 nanoseconds, and it is smaller than this maximum value specified here, right? So let's move to here. So 45, 45, 90, plus 135, right? That would take 135 to service A3 here. And 225 minus 135 would be 90 nanoseconds, right? So these two, the service time of B3, B2, and B3 here would take 90 nanoseconds. So both are misses, right? Because if any of them is a hit, the sum would be already smaller than 90 nanoseconds. So this is miss, 45, 45. So the only one remaining is B3 here, right? We still have to determine B3 here. Let's calculate the execution time again. 45, 45, 90, and plus 60 would be 150 nanosecond here. Is there any other way to reason about B3? From first ready, first come, first serve. Anyway, we cannot guess if B3 is a hit or miss, because this is channel 1 that determines the stall time, right? So we should think more here. If there is any other way to reason. Yeah. This is the time for break. Let's have the break, and we can discuss determining B3 after the break. Yeah, and then I can think more why I cannot determine this right now. Okay. So we will have a break for 10 minutes. Final word for this request B3 in channel 0. We think that both hit and miss are correct answers for B3. It could be either hit or miss. We don't have any means to reason that if it is 100% miss or hit. Any questions? Okay, we can answer the next question. This is question 5.
Okay, let's continue with the other question. The 5th one on branch prediction. Can you see it? Shall I zoom in a little bit? Okay. I don't know how to zoom in anyway. Okay. So this question is on branch prediction, and here at the beginning it defines an in-order pipeline with 12 stages. So everything except the branches is ignored, meaning you don't need to care about data dependencies. You assume that there are no data dependencies, or data dependencies are somehow resolved, right? Either by data forwarding or using some other techniques. Yeah, you have 12 stages in this pipeline, but it is unknown at which stage the conditions of the conditional branches are resolved. So it is actually what the first part is asking. So in an example workload with 1,000 of dynamic instructions, can you see the green? Yep. Yeah, so an example workload with 1,000 dynamic instructions complete at 2,211 cycles. And you know that 200 of the 1,000 instructions are conditional branches. And it asks at which stage the branch instructions are resolved. So here, some of you answer this question as how many bubbles are introduced to the pipeline on a misprediction, but the question asks at the end of which stage the conditions are resolved. So if you have answered this question as, so the answer is 7, right? At the end of 7th stage, the branches are resolved. I'll show how. And it introduces 6 bubbles to the pipeline. If you have answered 6, you'll just get a minor reduction in the credits. So it is, I think it was either 2 or 3 credits, something like that. So it's not a big issue. Okay, so how you find this? Maybe you remember it. I think Onur covered it in some of his slides. So basically, what we do here is we take into account the pipeline latency, right? So the pipeline is initially empty. All stages are empty. There will be some cycles where you fill the pipeline, and after that, if you don't have any mispredictions at each cycle, you'll retire one instruction. So basically, the formula is since the pipeline consists of 12 stages, the latency will be 12, right? The first instruction will be committed after 12 cycles. And we have 1,000 instructions. So plus 1,000. But we'll also need to do -1, right? And this minus comes from the fact that here, when we wait for 12 cycles latency, one of the instructions is executed. It is finished, right? So it is actually, so this is this latency accounts for the first instruction, and the next 999 instructions take this much latency. And then we also need to take into account the branch mispredictions. Yeah, so here we have 200 branches, right? And assuming that, so here conditions are evaluated. So here we don't do any misprediction, right? So the pipeline is stalling on a conditional branch. So each of those 200 branches will introduce some, let's say, M cycles of additional latency. Yeah, and this equation should be equal to the total execution time in terms of cycles. And here, if you do the math, you will find M is equal to 6. Right? So here in this pipeline, for each conditional branch, we have 6 bubbles, which means at the end of the 7th stage, the branch conditions are resolved. Okay, I think that's clear, since most of you have answered this correctly. Okay, so the next one, for the next part, we here give you an example assembly code. So first you will need to analyze this code to figure out how many branches are there in this code and how many instructions are executed in total. And based on the total execution time of 115 cycles, you'll need to find out how many mispredictions are made in this program. So here you have some mysterious prediction mechanism, which you don't know what it is. Yeah, so so the approach here is first finding how many mispredictions are made by this mysterious branch predictor, and after that, you'll evaluate each of those potential branch predictors and find out if one of those or multiple of those can be the mysterious branch predictor. Okay, So this is a fairly simple code where you have two loops. Right? So this loop 2 is the inner loop, and loop 1 is the outer loop. So if you look at those branch equal instructions, what they do is, so this one checks for R1 equal to 5. Right? If it's equal to 5, it jumps here, which ends this piece of code. And the other loop does the same when R2, which before entering this loop is set to 0, is equal to 3, and it jumps back to loop 1, right? So here what happens basically is those 3 instructions are executed 3 times, right, for this inner loop, plus this branch equal is executed 1 more time at the end to jump out of from this loop 2 and go back to loop 1. Yeah, so here for this inner loop, we'll have 3 instructions executed 3 times over 3 iterations plus 1, right? And then for this outer loop, similarly, this executes 5 times in total. So this part, so here we have 10 instructions for this part, and here we have 3 instructions for this part. So 3 plus those instructions here multiplied by 5, right? So this will loop 5 times, plus 1 for this branch equal instruction, where we check it at the end of the iteration when R1 is equal to 5 and jump to last, right? And we also have this instruction and this instruction. So here, again, if we sum up these numbers, it will be equal to 5 multiplied by 3 plus 3 by 3 plus 1 plus this instruction, and the last time when this branch equals executed, plus 3. And here we have 10, 13, multiplied by 5, 65 plus 3, and that is 68. So we have 68 dynamic instructions here executed in total. And then if you replace the numbers here with the equation here, so basically it will become 12 minus 1 plus we have 68 instructions for this piece of code. And then this time, we don't know how many mispredictions we have. So let's say it is X this time. But we know how many bubbles each of those mispredictions introduce, right? So this will be multiplied by 6. Let's aim at B. And this will be equal to 112 cycles. And similarly, if you do the math here, you'll find B to be 6. So in this program, when you execute this program with this mysterious branch predictor makes only 6 mispredictions. And the rest of the question is pretty easy, actually, right? Based on the taken and not taken pattern of this piece of code here, of the branch instruction in the piece of code here, you'll need to find out if any of those branch predictors match the behavior of the mysterious branch predictor. So a simple approach for evaluating those potential branch predictors is writing down the timeline of those 2 branches. So here in this program, you have only 2 conditional branches, writing the outcome of this. So in this outer loop, when first entered, this will be not taken, right? So 5 times in a row, this branch equal will be not taken. So when solving this, I did this. So I wrote not taken. So this is for the first branch. And in the second row, I was writing the outcome of the second branch equal this one. So this is not taken for the first iteration, and then we iterate 3 times here, right? We do 3 times not taken, and then 1 time taken. And this repeats 5 times. So writing this way separately will help you actually with answering some other. So it is not useful for the static branch predictor, but it will be useful for other predictors where you predict based on program counter, right? So this is why I don't write those in a single row. Anyway, we do that 5 times, and then T, and in the last iteration, this branch is taken, and this piece of code is being entirely executed. Okay, so we will use this to answer the questions here. Okay, so the first branch predictor that we need to evaluate is a static branch predictor, and we'll need to answer if this could be the mysterious branch predictor. If yes, which configuration, or you can maybe select multiple configuration, satisfies this answer, yes, if this is yes. Yeah, so this is quite simple, right? Static branch predictor, it is either always taken or not taken. So if you look here, if you do always not taken, we see that we have 1, 2, 3, 4, 5, and 6 takens, right? So we'll only mispredict those takens, but not taken paths will always be correctly predicted. So this static branch predictor could be the mysterious branch predictor, which is already implemented. So the answer is yes, and the configuration is always not taken. If we do always taken, then we'll have a lot of misses. Basically, all not takens here. What is the number? 5 by 4, 20 mispredictions will be made. So it is what actually you needed to put in here in the explanation. Okay, and then last time branch predictor. So here we will need to consider 2 configurations. The first one is the initial direction for prediction, and the second is whether it's local or global predictor based. So you have a lot of stuff to evaluate here, but probably it didn't take too much of your time during the exam, because I mean after having such a table here, it is quite easy to evaluate. So if you consider the local case with the initial taken direction, what will happen is we'll do here miss for this branch instruction. So we consider 2 branch instructions separately here in this local last time based predictor, right? So this one will miss, this one will hit, and here we'll have 1 more miss, right? So after this one, the last time predictor starts to predict not taken, so it will predict this correctly, until this. And for the last iteration, this taken path will be mispredicted. So we'll have 2 mispredictions here. And again, starting here with taken prediction, it will mispredict this, then it will mispredict this, and mispredict this. So we already had how many? 2 here and 3 mispredictions here, and then it will keep mispredicting those 2, right? So we clearly have more than 6 mispredictions for local and taken direction. If you evaluate not taken initial direction, you will see that you have a lot of mispredictions too, more than 6 mispredictions. So local could not be the configuration that behaves like the mysterious branch predictor. And then you do the same for global. For global, again, so for the last time predictor, won't work very good for this kind of branch pattern, right? Because you always have here back-to-back taken and not taken, which will be always mispredicted. Yeah, Yep. So in the global, no matter what is the initial prediction, this one and this one will always be mispredicted. And then this one and this one, those will keep being mispredicted, right? Independent of what was the initial prediction. So clearly you'll have more than 6 mispredictions. So this last time branch predictor cannot be the mysterious branch predictor at all. So there's no configuration that satisfies that. Backward taken, forward not taken branch predictor. So here we have only, actually the first branch here is a forward branch, and the second one is backwards branch. And the forward will be not taken, and backward will be taken. So the first one is forward, second one is backward. So since this is predicted as taken, for this second branch, every not taken path will be mispredicted, and we will have more than 6 mispredictions. So this was, again, very easy to evaluate. The answer is directly no. Yep. And the last one, 2-bit counter-based predictor. Probably this was the most complicated one. So here the answer is yes, and we have more than one option that satisfies the 6 prediction case. And the reason is basically when you have this 2-bit counter based predictor and start with those 2 cases, either of those 2 cases, it behaves like it behaves like static always not taken branch predictor, right? So if you consider, let's say, 0, 0 and global option here, since initial direction will be not taken, this will be correct, this will be correct, this will be correct, this will be correct. This will be wrong, but this will be correct, right? So again, only taken paths will be mispredicted. So this global with strongly not taken or weakly not taken satisfies the behavior of the mysterious branch predictor. There might be some other options. For local, I think that there's no configuration that satisfies, but if you have found anything, you can share. But I think it's only the global and those 2 options. If you select one of those 2, you'll make one additional misprediction at the beginning for weakly not taken or strongly taken. Oh, sorry, the answer is this or this. So it should be strongly not taken or weakly not taken. But if you start with weakly taken or strongly taken, you'll make one additional misprediction at the beginning, which will result in more than 6 mispredictions. Yep. Okay, let's evaluate that. Strongly not taken and local. So for this one, this will be a miss. For this one, this will, yes, that's true. Yeah. Local and strongly not taken also satisfies, yeah. Yeah, weakly not taken, yeah. So it doesn't matter whether you choose local or global, actually, if you choose one of the not taken initial values, yeah. Any other questions? Okay, cool. Can continue with the next one.
So this is question 6, SIMD. I will try to go quickly to cover more questions. So the question says, we have two SIMD engines, a traditional vector processor and a traditional array processor. Both processors can support a vector length of up to 16. All instructions can be fully pipelined. The processor can issue one vector instruction per cycle, and the pipeline does not forward data, so there is no chaining. So we simplify the problem, so we ignore we only take into account the latency of the execution states, so we ignore the decode states and the write back. So these are the latencies of each instruction. So more considerations. All the vector instructions operate with a vector length specified by VLEN. The vector load instruction loads VLEN consecutive elements from the destination address specified by the value in the destination register. The vector store instruction stores the VLEN elements from the source register in consecutive addresses in memory, starting from the addresses specified by destination. So both processors have 8 vector registers, which can contain up to 16 elements, and 8 scalar registers that are these ones. The entire vector register needs to be ready before any element of it can be used as part of another operation, and the memory can sustain a throughput of 1 element per cycle. The memory consists of 16 banks that can be accessed independently, and a single memory access can be initiated in each cycle. So the memory can sustain 16 parallel accesses if they all go to different banks. So the first question is, which processor, array or vector processor, is more costly in terms of chip and area? So the answer is the array processor, because it requires 16 array processor, because it requires 16 functional units for an operation, and the vector processor only requires 1. So the next question is, the following code takes 52 cycles to execute on the vector processor. So we have these 3 instructions. These are dependent instructions. Yeah. So we can, so just to visualize this, so we can, in a vector processor, we can issue 1 instruction per cycle. So for example, in the add, we have the add here, and we can issue the next add in the next instruction, and so on. So we will have at the end something like this. The latency of the add, according to the table, is 5 cycles. So we'll have for executing the first instruction, we will have 5 cycles here, plus this number of cycles, that is the VLEN minus 1. So we have then 5 cycles plus VLEN minus 1. So the next instruction is exactly the same. So we have, again, 5 cycles plus VLEN plus 1. And the multiplication is the same thing, but in this case the latency is 15 cycles plus VLAN -1. Yeah, and this is equal to 52. So if we do the math, we have VLAN equal to 10. So how long will the same code execute on an array processor with the same vector length? So in array processor, we can execute all the add operations, in this case, in parallel, the same with the next instruction and the same with the multiplication. So we have 5 cycles for the first instruction, plus 5 cycles for the second instruction, plus 15 cycles of the multiply. So it's 25 cycles. Any questions until here? So the next question, we have this piece of code with loads and stores. We are accessing memory in this case, and this takes 94 cycles. So we assume that the elements load in BR0 are all placed in different banks, and that the elements loaded in BR1 are placed in the same banks as the elements in BR0. So similarly, the elements of BR2 are stored in different banks in memory. What is the length of the instructions? Explain your answer. So just to visualize again, we have so we have 16 banks. So we have, just to visualize, the first load can be executed like this. We can issue one operation of the vector per cycle. So we will have, at the end of this first load, we will have 20 cycles for the load plus VLAN -1. And the second load can be issued after. So when this bank, when this is free, we can issue another operation here. So this is for the first load, and this is for the second load. So at the end, we will do both loads in 20 plus 20 plus -1. So for the add and for the shift is the same than in the previous case. So we have the add is 5 cycles plus VLAN -1, and for the shift is 1 cycle plus VLAN -1. So on the last store, so we have 20 cycles plus VLAN -1. So the tricky thing here was these first 2 loads that can be done in this amount of cycles. Any questions here? So on the third question, the D question here, we have the same code than before, and this take. Oh, first I have to apologize because this was wrong. It's not 1,063 cycles. 163 cycles is 170. But if you reason well about the question, we will give you the full mark if the reasoning is okay. So the question is, we replace. So now we have a different memory module. So with a new with unknown characteristics. So so we execute the same code, and the VLAN in this case is 16. So the elements loaded in BR0 are placed in consecutive banks. The elements loaded in BR1 are placed in consecutive banks also, and then elements of BR2 are also stored in consecutive banks. So what is the number of banks of the new memory module? So just to visualize again, I'm going to plot here. So imagine that we have 16 banks. So we can issue our loads like this. So we will have at the end, this is the latency is 20, and this is with 16 banks, this is 15, that is minus 1. So this is with 16 banks. So what happened with 8 banks? Well, first we assume that the number of banks is a power of 2, because if not, it's very, for example, for mapping the addresses, physical addresses to the banks doesn't make sense, right? So for 8 banks, so we will have something like this. So we have 16 elements, and we access the first 8. 1, 2, 3, 8, and here, and the next 16. So as only we have 8 banks, we have to access 2 times each bank. So the total latency this time will be 20 plus 20. Here is, well, in this case is 7. That is, well, this here is wrong. It's not VLAN, it's banks. I'm sorry. The same thing here, banks minus 1. And with 4 banks is something similar. So in general, we can say that the latency of these loads is 20 per 16 divided by the number of banks. So that is this. So we have 20. If the number of banks is 16, so we multiply 20 per 1. If it's 8 banks, we multiply 20 by 2. So if it's 4 banks, we double the latency. So we have the same thing for the next load. It's 20 plus 16 divided the number of banks, plus this thing here, what we calculate, banks minus 1. So the reason is similar to the previous one in this case. And then the add and the shifts, and the shift, the add is 5 cycles. Plus minus 1. The shift is 1 cycles. Minus 1. And then another memory access, the store in this case is the same, is 20 plus multiply by 16 divided by the number of banks plus banks minus 1. So in this case, VLAN is 16, and if you do the math, nobody did the math in the exam because this number was wrong. But if you reason well about the number of banks and how this affects the number of cycles, so we gave you the full mark if the reasoning is correct. But with this new number, with 170, we have that the number of banks is 8. You have any questions here? Some of you reasoning well about this question, and at the end you couldn't solve it, but it's okay, of course.
Okay, let's solve now question 7. In DRAM bitmap indices. So this question is about Ambit. You're familiar with Ambit, right? I think it was one of your required readings. So the question, probably, it's easy, right? The most difficult part is reading all this text here, I think. It says, recall that in class we discussed Ambit, which is a DRAM design that can greatly accelerate with bitwise operations by providing the ability to perform bitwise and or of 2 rows in a subarray. One application that can benefit from Ambit is the database bitmap index. So with this application bitmap indices, we can run queries on a database. For example, the query that we are going to run in this exercise is actually how many unique users were active every week for the past W weeks. Every week, for each user, we are going to use 1 single bit. So given the value of this bit for a given week and for a given user will be set to 1 if the user actually was active in that particular week. And the total number of users is U. We are going to assume that the bits corresponding to 1 week are all in the same row. But it might happen that U is greater than the total number of bits in 1 row, that you know it's 8 kilobytes. The row size that we are going to consider is 8 kilobytes. So more rows in different subarrays are used for the same week. Assume that all weeks corresponding to the users in 1 subarray fit in that subarray, so that we don't need to store bits from the same user in different subarrays. That's what this means. And we want to compare 2 possible implementations of this database query. One of them is CPU-based, the other one is Ambit-based. And for the CPU-based, what we need to do is moving all the bits from the U users and the W weeks to the CPU. And in the CPU is where we are going to AND the bits corresponding to the past W weeks for every user. And finally, we will perform a bit count operation to obtain the final results. We will obtain the number of users that were active in all the W previous weeks. Because this operation is very memory bound, essentially here what we are doing is accessing memory, executing the AND operation, which is expected to be very lightweight, and also the bit count. So the way we are going to simplify the calculation, or the way we are going to estimate the execution time is by just considering the data transfer time, the memory access time, right? And the memory bandwidth that the CPU can have to memory is X bytes per second. So that's what we need to know to calculate the execution time for the CPU-based implementation. For the Ambit-based implementation, because Ambit is able to execute R and OR operations in DRAM, and bulk bitwise operations in DRAM, and the operations that we need here are bulk bitwise operations, we can perform the AND in memory, and when we finish, we will have a very large array with 1 bit for every user, and this array must be moved to the CPU so that the CPU executes the bit count. And same as before, because the bit count is very lightweight, for this bit count we are going to consider that, so that we are going to estimate the execution time of this bit count by just considering the memory access time. So part A of the exercise says, what is the total number of DRAM rows that are occupied by U users and W weeks? The first thing we are going to calculate is the number of subarrays that are needed. You know that we have users, and in each subarray we can have the bits corresponding to a certain number of users, and the number of users is 8 times 8k, because 8 kilobyte is the number of, so it's the size of the row, and 8 is the number of bits per byte, and this is the field of this, is the total number of subarrays. And for the total number of rows, it's going to be easy because it's the total number of subarrays that we have just calculated times the number of weeks. Okay? Part B says, what is the throughput in users per second for the Ambit-based implementation? Well, in order to calculate the throughput in users per second, the first thing we are going to calculate is the total execution time. The total execution time for the Ambit, let's call it T Ambit, is going to be the total time that we need for the AND operation plus the total time that we need for the bit count. So for the AND, for the total AND operation, this time is calculated as the number of users, so it's the number of rows that we obtained in the previous, previous part A times W times the time that we need to compute or accumulate the bits in each particular row, in every row. And as the question explains, for every row, we need to row clone, we need to copy the row to the operand row, and then we need to calculate, so perform the Ambit AND to accumulate in this accumulation row. So remember that here we have operand row and accumulation row. So this total time per row is TRC plus T AND. So that's the way we calculate the total, so the time for all the AND operations for all the rows. Once we have finished with all the AND operations, we have to perform the bit count operation. And as we said before, we are only going to, so we are going to estimate this time as the time we need to move the corresponding bits to the CPU. And this is the total number of bits, or the total number of bytes, which is U divided by A divided by X, which is bytes per second. So this is U divided by A byte divided by X. So finally, this is U divided by X times 8 seconds. So total Ambit time is the addition of these two, and for the throughput, it is the total number of users, U divided by T Ambit. And this is in users per second. Okay? So this is part B. And part C, let me know if you have any questions. In part C, we are going to do the same calculation for the CPU implementation. And for the CPU implementation, as the exercise, as the question says, for the CPU implementation, the way we estimate this TCPU is by just considering the time necessary to move all the bits to the CPU. And this is the number of users times the number of weeks divided by 8, so that this is number of bytes, and this is divided by X, which is the memory bandwidth bytes per second. It's as simple as that. So this is U times W, 8 times X seconds. So the throughput of the CPU implementation is the number of users divided T CPU users per second. And finally, part D says, what is the maximum WB for the CPU implementation to be faster than the ambit-based implementation? Assume that U is a multiple of the row size. So, well, here, what we need to consider is the case where TCPU is less than T ambit. So after doing that, we just need to we just need to obtain W, and so finally, if you elaborate this by yourself, you will find that W should be less than 1 divided 1 minus X divided 8K times TRC plus T and. So it's the total number of weeks that we want to consider is as small as this. Then it is better to execute this query on the CPU side, right? That's the idea. But as you can see, the question is quite simple to solve. Probably it's more difficult to understand what this is about and know how ambit works. That is something that you should know after attending the lecture and after reading the paper. And besides that, the calculations here are very, very easy. Any question? No? Okay. Thank you so much.
Okay, last question, and we have only 10 minutes, so we'll go very quickly over this. So this question was bonus, and many of you didn't even attempt to solve it, but actually most of the parts of these questions were relatively simple. So maybe next time, for the next exam, you may want first to skim through the questions, right, and mark questions that will take more time and start with the simple questions. Probably you run out of time, right? That's why you didn't probably attempt at this question. Yeah, anyway, so this is, as the title indicates, about caching and processing in memory. And in this question, we have a short piece of code which is traversing two arrays, A and B, and the starting addresses of those two arrays are given. Yeah, and then the processor here, we assume that only suffers from the latency of the load and store operations, right, the memory latency, and we ignore everything else. So in the first part, it asks what's the execution time of the piece of code here, and for the memory accesses, we have 50 cycle latency. So with those constraints given this question, what you had to do was only counting how many loaded and store instructions are there and multiplying it by 50. And this was like 15 points worth of question. And here basically what happens in this inner loop is it iterates twice. So each of those load instructions are executed twice, and we have one store instruction. So, and this is one iteration of the outer loop. And the outer loop is executed 16 times. Right, so here the calculation is pretty simple. 16 multiplied by 5 memory instructions multiplied by 50 latency of the memory accesses. And here you will find that it is equal to 4,000 cycles. Is that correct? Yep. Okay, so it's on the back. Yeah, so it was the first part. And the second part is kind of a little bit more difficult because it defines some cache, and you'll need to consider when accessing those two arrays A and B, whether you get a conflict or not. So based on whether the data fetched to the cache conflicts, you will get hits or misses for the next accesses to the same data. So it is longer to solve and requires more thinking. So I will do what you needed to do during the exam, right? So I will skip this part, and I will continue with C. So if you look at C, so here the things change a little bit. So basically here it says that even with caching, you are not satisfied with the performance, so you consider executing the same piece of code in some processor unit close to the memory, which has 10 cycles latency for each access. So here it is basically the same calculation as here, right? But instead of, wait a second, something should be different here. Latency for both trees, how many cycles does it take to the same program using in-memory computing? Memory to this. Yep. So here basically it's the same as this equation, right? But instead of multiplying by 50, you had to multiply by yeah, you need to multiply by 10. Yeah, which is 16 multiplied by 5. We have 5 load store instructions for each outer loop iteration, and we multiply it by 10 cycles latency. And here basically the answer is 800 cycles. So it was about this part. And then for D and E, so in D part, here you need to consider whether changing the cache capacity will help to improve the performance for B such that the performance is equal to the in-memory processing case. Right? So basically it asks, if possible, what should be the new cache capacity to get the same performance as in-memory computing. So since we didn't solve part B, this might be more difficult. Yeah, so let's take a look at B. Yep, and same for E. It is also coupled with part B. Okay, so if you look at part B, so it says that the cache capacity is 128 bytes, and each cache block is 8 bytes. So that means you have 16 cache lines that you can store in the cache. And the cache is direct mapped. Okay, and if you look at those base addresses again, you'll see that those two addresses map to the same set in the cache. So both of them, if we draw the cache like this, first elements of both caches, of both arrays map to the first set, to set 0. So I'll go quickly over this, but so basically if you look at this program, what happens is in the first iteration, element 0 of A is multiplied by element 0 of B, and then A1 is multiplied by B1, and then those two multiplications are summed up. And then in the next iteration, B remains the same. Again, B0 and B1 is accessed, but A is incremented by 1. So in the second iteration, A1 and A2 is accessed. In the next iteration, A2 and A3 is accessed. So this is yeah, it is a fairly simple computation and piece of code, right? Probably it shouldn't be too difficult to understand. But anyway, so what happens is we need to consider how those accesses will map to this cache. So first, A0 is accessed, so A0 is placed here, and then B0 is accessed, right? So if you trace the code, so this is a load for A0, this is a load for B0. Since A and B conflict in this cache line, this A0 will be replaced by B0, and you'll get a miss. Basically, if you trace this down, you'll see that only for the first cache line, because B0 and B1 map to this cache line here, to this set here, only for the first few iterations, you get conflicts and irregularity in the hits and misses to the cache. But after that, B accesses to B always hit, and accesses to A hit and miss, because with each cache line, you'll fetch 2 elements of A. And we provide a quite detailed solution for that, so we'll ask you to go over it by yourself. So it is already online. I hope the amount of detail is enough here. If you have questions, we can you can post them on Moodle. We'll be happy to answer. But basically, what happens is, yeah, so the answer here will be 900 cycles, but one interesting observation here is that with those 2 base addresses for A and B and direct mapped cache, it is not possible to eliminate the conflicts for the first few iterations, right? And it is, and the question in part D was, is it possible to improve the performance by increasing the capacity without changing the cache line size, right? So you just add more sets. And the answer will be no, because you'll get the same conflicts no matter what's the size of the cache, unless it's too small, where you will get more conflicts and the performance will be lower. Yeah, so it is not possible to make this faster. So the answer here is no. And then what other changes could be made? And here you can answer like, basically you can change the associativity of your cache. If instead of direct map cache, you employ full associative cache, you'll get a better hit rate and better performance. Yep, that was the last question. Thank you, and hopefully see you in the final exam.